good to see all of you again. So, any questions from last time? Okay, so shall we get started then? What I'll do now, and I'll usually do this every time, is I'll start with what we covered in the previous class. So, we had essentially an introduction to the course. So, let me just go over again. I am the instructor and Niladri is the TA. And then, we discussed a little bit about, what type of things are granular materials like sand, gravel, various kinds of minerals, grains, and other sort of food items. And then various other things like catalyst pellets, tablets, processed food, cement, fertilizer, bulk chemicals. So the huge amount of material comes under this granular materials. And what I said is that more than 50% of the products are granular of our industry. And of course, if you look at mineral and all those industries, it's huge, the amount of granular materials processed. And even if you look at things like raw materials and catalysts and absorbents and so forth, all come under this category of granular materials. So what the basic point is that handling of these kinds of materials and processing them is very important in a number of industries. And this is like huge industries like cement, fertilizers, minerals and mining, steel making, agriculture, food processing, ceramics, pharmaceutical manufacture, polymers and construction. So this is just a subset of, but you see a lot of handling and processing of granular materials in industry. So what we are learning is of practical importance. Also, in nature, we see them in a number of different applications. And so very often you will see that it's not just engineers who are trying to study granular materials, but geophysicists and, others, civil engineers and so forth are also very interested in granular materials. So if you look at what are some of the unit operations, and we had seen these also. So if you have no fluid effects, that is, the particles are large enough so that the presence of the air in between the particles is negligible. So you can have operations like sieving, storage and flow from bins. So here's some example of storage in bins, heap formation and then mixing and blending, conveying, crushing and grinding. This is one example of that. And of course, reactions. So there are many solid state reactions that are done. And this is one example of a reactor. And it's a cement kiln. This is a rotating cylinder, and there's partly filled with the raw materials to make cement. This thing rotates around its axis. The material is fed from here, from these huge hoppers, and then it comes out. You can see the scale of this, it's massive. So this distance is 100 meters. So there are many examples. Here just I was saying that in steel making it's very important. So one example where it's important is, for example, the core process of steel making, which is the blast furnace. This is actually just a big reactor, which is a packed bed, and the material is just heated. This is coke, iron ore and limestone are added from the top, and then hot gases go from the bottom, and the reaction takes place, and then you get molten iron coming out. So this is also an example where granular processing is very important. But I tried to also explain that though this is a very, very important area, the development of granular mechanics has really lagged, let's say, a field like fluid mechanics. And here are some of the major developments that took place in fluid mechanics. But the key thing is that the governing equations for fluid flow, which are the Navier-Stokes equation, were developed in 1800. And we still don't have any such equation for granular mechanics. But many advances have been made, and these are some of the things that I mentioned, that we have DEM, which is a good method of simulation from the 70s, and this Bagnall's work, kinetic theory equations, and now for dense flows, some empirical equations have come. So there has been a lot of progress, but it is not as mature as fluid mechanics. So then we discussed what we would cover in the course outline, and then I started talking about the characterization of granular materials. And it's really important to characterize them, because most granular materials are irregular in shape, except of course seeds are quite regular, or even man-made pellets, or they are quite regular. But otherwise, most of the particles are irregular because they're made by crushing and grinding and so forth. And usually one particle differs from the next one. Even seeds are not exactly alike, they're slightly different. And the flow and mechanics depends on both particle size and shape. So we have to characterize them. So if you get a certain behavior for one type of material, then if the shape or size changes, then the behavior could be quite different. So characterization is very important for repeatability, and if you're doing science. But if you are making anything in industry, then it's very important for quality control. So if your size suddenly changes, then the behavior of the material will change. So this is quite important in quality control. And then if you want to characterize, let's say if you're given a huge pile of material and then you have to characterize it, then there are many steps in it. The first is sampling. You have to be able to sample in a proper way so that you get a representative sample. So there's a lot of literature on that, how to sample. Then you have to do shape characterization, and we started talking about that. And then size measurement. So what we saw is, you can do a qualitative classification of shapes. So now I've put pictures of everything we discussed. So you have needle-shaped things like rice husk or angular. This is gravel. You can have crystalline. This is salt. Or fibrous. Here's a picture of jute. You can have plate-like. Here's some mica pictures. You can see the plate-like structure. Dendritic or branch. So you can have particles that are like this. And then rounded or granular, which is sand. And then of course you can have man-made things like spherical beads, so glass beads. And really the shape makes a big difference. When I just talked, I was talking about this idea of sphericity, which is a quantitative way of saying how round a particle is or how close to a sphere it is. And as we saw last time, The sphericity is defined as the ratio of the surface area of a sphere of the same volume as the particle to the surface area of the particle. Supposing the volume of the particle is Vp and the surface area of the particle is Sp. Then the diameter of a sphere which has the same volume is given by this expression, where dE is the equivalent diameter. And so if you rearrange, you will get dE is just 6 times Vp by pi raised to the power of 1/3. And so if you now want to calculate what is the sphericity, then this is the diameter of the equivalent sphere. The area of that sphere is just pi dE squared, and then you divide by the surface area of the particle, which is Sp. So this ratio will give you the sphericity. Now, if you have geometrical objects, let's say, for example, if you had a sphere, well, then the ratio of these two will just be 1. A cube also comes pretty close to 1. So, these have a sphericity of 1. But if you take sand, it may have a sphericity of 0.82. That means it's just a slight deviation from a sphere. And if it's an angular particle like gravel, then it can go to 0.65. Whereas if you have flaky material like mica, then that sphericity goes to 0.2. So the basic point is that the highest value for the sphericity is 1, and that corresponds to a sphere. And the reason for that is the sphere has the smallest surface area. The surface area per unit volume for a sphere is the smallest, and everything else is larger. So this is always going to be less than 1 unless you have a sphere. So this is one way of characterizing the shape of a particle. Okay. Next, let me go back to this. And let's start something new today. And think of some more quantitative ways of shape characterization. So we've already looked at sphericity. And another way that is very commonly used for shape characterization and here we are talking about quantitative methods of shape characterization. And the way that we often do this is through what is known as image analysis. So you basically take an image of a particle . So let's say there is a digital image of a particle like this, and you can actually digitize, because this is a digital image. What this is actually, the way the image is actually stored is this whole thing is just divided into tiny squares. So the image is not actually a continuous thing, though from our eyes it looks continuous, but it's divided into these small squares, which are called, does anyone know what these are called?
Pixels.
Pixels, yeah. So all your cameras have so many megapixels. Mega means 1,000. So if it's 12, no, mega means million. So if it says 12 megapixels, that means that there are 12 million such squares in your screen. But in general, depending on the resolution of your camera, this is what it is. And so each square will have a number associated with it. Or it may have 3 numbers or 4 numbers. So if it has a single number, let's say it's a black and white thing, then that number will go from 0 to 256, where 0 is black and 256 is white. So that way you can essentially have a number at each point in the image, and through an analysis method you can actually identify the boundary. There are many ways that people do it, but for example, they may just take a numerical derivative of the image, and wherever there is a sharp change in the intensity, which is this number, this is the intensity there. So if there is a sharp change in the intensity, you will get a peak, and that will identify your interface. So there are many ways of doing it. We are not going into the actual details of image analysis, but let's say you can get what is the edge of this, and so for you will be able to get the coordinates of the boundary points xi, yi, and let's say you can then calculate the centroid, which is given by xc, the centroid x position is just sigma xi, I going from 1 to n. Let's say there are n points on the boundary into 1 by n. So this is the mean x position, and similarly the y coordinate for the centroid is 1 by n y. So you'll have the centroid positions, and n is of course the number of points on the boundary. And then we can actually even define the radius at each point. Let's say this, we call it as r of I. Then Ri can easily be defined. Ri is the distance from the centroid to the boundary, and that can be defined as just xi minus xc whole square plus and we can also get the angle theta I, that is just tan inverse of yi minus yc divided by. So what I'm trying to explain over here is that once you have a digital image, then you can do various kinds of operations. You can find out what is the boundary positions, then you can find out the centroid, you can find out what is the radius as a function of the angle. You can find out, things like, very important for this might be the aspect ratio, which is R max to R min, so the maximum radius to minimum radius, could be the aspect ratio, usually called lambda. So many of these things can be determined. So this is the basic concept of image analysis, that you have an image, you can, through some processing, identify, let's say, the boundaries of the particle. Then once you know the boundary values, then you can get things like the radius of the particle and so forth. So obviously this is just a projection. I mean, there will be other more sophisticated techniques where you can get the third dimension also, and that is certainly possible. And so this is one way of doing it. You can actually do aspect ratio. Then there's another way that you can characterize it. They call it harmonic analysis. So this is nothing but Fourier analysis of the f of r versus theta data. So what we can do is, now we have Ri data and theta I data. Then can we sort of write it as, instead, as a Fourier series, which is something like A0 plus sigma n is equal to 1 to n. Let's call this something different from n, maybe 1 to m, where m is the number of modes that we are interested in. So in other words, we want to describe this shape by this function. So A0 will be the mean radius, and then you want to try and get all the deviations from a sphere in terms of a sum of different cosines, and the order of the cosine is increasing. So you have n equal to 1, 2, 3, 4, 5. So you'll pick up more and higher frequency deviations from this. And so if we want to fit this function to the data Ri, theta I we have got, then this is quite easy. And the way that one can do it is, one can easily get these coefficients um, by doing a small sort of expansion. So I'll give you the result first, and then tell you how to get it. So A0, this is equal to A0 is equal to 1 by 2 pi integral from minus pi to pi of r of theta d theta, which of course can be simply written as 1 by 2 pi sigma I going from 1 to n r of I delta theta I. Okay, so you can replace the integral by a sum, and these Ri values we know and theta I values we know, so we can easily calculate delta theta, which is, let's say, theta I minus 1 or something like this. And similarly, we can get An as just equal to, and this An is equal to An cos of phi n is equal to integral from minus pi to pi r of theta cos theta And then this also can be replaced by a summation and I can write down Bn is equal to An sine of phi n. Okay, so this is the way to do the analysis, that you'll get An, Bn, and then from there you can get capital An, phi n, and so forth. So you'll be able to get all that. So how did I get it? Well, the first thing is, if you expand this out, so let me just go backwards a little bit and show the derivation for these three things that I have written down. And this you can remember your math course a little bit. So I can write down a theta, r theta is just equal to a0 plus sigma n equal to 1 to m. And when you open out this, it's an cos of n theta cos phi minus an sine of n theta sine of phi. Correct? So this is what it is when you expand it. So then you will get an, and I'm sorry, this is minus over here. So this is the first step. I expanded out this, so you have this. So now, as a simplification, I'm writing this as equal to a0 plus sigma n is equal to 1 to m, and this will be just an cos of n theta plus bn sine of n theta. Okay, so this is the first step. Then what I can do is I can multiply throughout by cos of n theta. So if I multiply throughout by cos of n theta, so I'll do integral r of theta cos of n theta, or let's say cos of small m theta d theta, from minus pi to plus pi. And then on this side I will get integral a0 cos of m theta d theta. I'm not writing minus pi to plus pi, you can understand it. All the integrals are from minus plus pi to, and then plus sigma an cos m theta cos m theta d theta plus bn cos, sorry, sine n theta cos m theta integral. Okay, so this is the integral. Now, since the integral is from minus pi to pi, one of the results that I'm going to put down are, these are the results you can see in any sort of table of integrals. What it says is sine of n theta cos of m theta d theta is equal to 0 no matter what is the value of n and m. For n and m being integers, this term is always 0. So you can see that this term goes to 0. Then other result is that if you have integral from minus pi to pi, I'm sorry, so if this is 0, then even this term is 0, because this corresponds to sine of theta equal to sine of n theta equal to 1. That is also 0. Then sorry, let me leave this right now. So the other term is that you have cos of n theta cos of m theta d theta. Now this is not equal to 0. This is equal to 0 if n is not equal to m, and it's pi if n is equal to m, and it's equal to 2 pi if m is equal to, I'm sorry, yeah, if m is equal to 0. So this is all for m greater than 0. So this is when m and n are both 0. Let me just write it properly. This is all for n greater than 0, n equal to 0, and any value of n. So then this term now with this, so if m is equal to 0, then this is just a0 d theta integral from minus pi to pi, so that will become equal to 2 pi. So this term is 2 pi only when m is equal to 0. And then finally we have sine of n theta cos of n. This is equal to 0 if n is not equal to m, and it's equal to pi if n is equal to m. So you can see that when I do this type of integral, all the terms will go to 0. So if m is not equal to 0, then this term is also equal to 0. And then I'll finally get this from this entire series of I going for n going equal to 1 to m. All these terms are 0 unless n is equal to m. And so when n is equal to m, this term will just give us pi. So finally what you get is from integral minus pi to pi, r raised to r of theta cos theta d theta is just equal to, from here I'll just get, the only thing that survives on the right hand side is just am into pi. So here there's a summation of n going from 1 to m, and all the terms in this series will go to 0 except when n is equal to m, and when n is equal to m, this integral is just equal to pi. So that's how you get this. So then you get 1 by pi integral from minus pi to pi r of theta cos theta d theta. Now if you look at this term a0, when m is equal to 0, this is nothing but 1 over here. So then you can just get a0 is just equal to, so if m is equal to 1, so this is just integral of r of theta from minus pi to pi, and over here you will have 2 pi into a0. So a0 gives you 2 pi into integral from minus pi to pi of r of theta d theta. So this just illustrates how to do it. I've only done the calculation for this, and over here I've made a mistake in this formula. There should be 1 by pi over here. Okay. So this is the derivation of the harmonic analysis, not directly related, but it just shows you that one can do quite nice analysis of, once you have this shape, then very sophisticated analyses can be done. And one of the ways that people analyze this is that they will plot the coefficients. Finally, once you have all the coefficients from your image, then what people have shown is that, let's say you can plot an divided by a0 divided versus log of n. And usually for many of the particles which are irregular in shape, you get a straight line on this curve with a slope s, where s goes usually between 1.3 and 2.5 for irregular particles. And what it says is, if smaller s means rounder particles. Okay. And this, I think we'll do some example on this so you can figure out. Okay. And now I'd like to just show you this little bit of this on a little bit about image analysis. So, digital images are composed of pixels, and each pixel has an intensity for grayscale images from 0 to 255. So we can have an intensity value at each xy position. We can identify edges, we can count particles, and so forth. And what I'll do is I'll put this small image dot pbm. So that's like part of a black dot. And I'll put this image file on Moodle. And then, once we have all these text files which have all the positions and the intensity values, then we can easily find out the XY positions for the perimeter, and then we can do harmonic analysis as I tried to show you just a little while ago. And here is this is what, I took a very small image file. This is just 50 by 50 pixels for that black dot. And this is because it's this very simple format. It just simply writes down as a series of numbers, and those numbers are either 0 or 1. 0 means black and 1 means white. And so from this we can get, this is essentially what the image file looks like in this particular case of .ppm, and I put this image file up. But we can of course look at the image and do it ourselves, or there are actually commercially available instruments where there'll be a microscope and the particles are all spread out like this on a plate. Then you capture the image, this will be a digital image, and then you do image processing. So this is, as I showed you, that the whole image has all these pixels in there. So you can identify which is the particle and which is not the particle by saying which is blacker, so the intensity values can be done. You can find the edges. You can do all sorts of analysis and result generation, like how I did. So these types of things are commercially available. You can buy them. But something that you can do without any cost is you can use some free software called ImageJ. This is a very powerful software that is available for image analysis, and you can download it from the net. And these are some of I've just taken the first few features that they have listed. Firstly, it runs everywhere. So it's written in Java, so it can run on Linux, Mac OS X, Windows, 32-bit, 64-bit, everywhere it can run. It's open source, it's freely available in the public domain, and no license required. So you don't have to pay anything to get it, it's free. It has a large and knowledgeable community with more than 1,700 users and developers. So, if you have any problem, you can just ask and they will tell you what to do. You can automate tasks and create custom tools using macros. And there are many plugins also. So, for example, Niladri, who is the TA for the course, is using some plugin for ImageJ to actually track particles moving. So he's got a movie of particles moving, and you can actually find the trajectory of those particles. Not only characterize shape and stuff, but you can also characterize the motion. So this is what I had to say about characterization of particle shape. And then I go back to the lecture, and this is where we had stopped here. And the next thing that I want to talk about, and maybe I'll just start the introduction to that, is about size measurement. So shape is of course important, but size is also very, very important. So what we have seen is, of course, that you have irregular shapes. So, if you have something that's not spherical, then you'll have multiple length scales. And by this I mean, something like, let's say if your particle is like this, well, what is your size? Well, there could be one size here, there could be another size here, you know, there could be many other sizes that you could define. So if you have an irregular particle, you have multiple length scales. And then, of course, the other thing to always note is that invariably no two particles are exactly the same. So you'll have multiple size particles, and they will be of different shapes. So this is what I'm saying is, this is the general case. Of course, if you start with glass beads and they're all spherical and all of the same size, that's a different story. But for most practical examples, you'll have everything varying. So the result is that, usually your measurement technique it will give you an equivalent diameter. So, it may be some sort of diameter that is related to the overall size, but not exactly that dimension. So there is an equivalent diameter. And what are those diameters? Well, if you are using a sieving process, then it will give you the sieve diameter. So this will tell you, okay, this particle can go through. A sieve is usually, uh, you know, just a grid like this, and so particles can go through only if they can fit through the holes in the sieve. So this particle may go through, when it's sort of oriented in a particular dimension, but if it can go through this, then that is the sieve diameter of that particle. Then you could have surface diameter. Okay, if your measurement technique is measuring the surface area of the particles, or you could have something called the drag diameter in case your particle is being measured. um, if your technique is measuring the sort of drag force that the particle exerts on a fluid and so forth. So usually for size measurements based on sedimentation techniques, this will give you the drag diameter. If you're using, let's say, adsorption of gas or something to measure the surface area and then the diameter, then you'll get the surface diameter and so forth. And there are a large number of methods, and if I just uh, you know if I just go to this and show you. So here are some examples. So the most common method, and for so here, let me paste this in here, and let's say this is in microns. So the most common way of measuring size is through sieves. Usually you'll have a number of sieves and one on top of the other. The largest opening will be on top, and then the smaller and smaller and smaller and smaller. So you put your sample on top, then the biggest particles on the top sieve, then the next biggest on the next sieve, and then so forth, and the finest are in the bottom sieve. So you'll get a range of sizes. These will be the sieve diameters. And typical sizes that you can measure go from 40 microns to actually you can go to very large sizes. And then if you have very fine particles, the thing is that as the particles become finer, then their possibility of going through the sieve becomes lower and lower. So then you can have air jet sieving where you're using air to push it through. Or you could use sedimentation, so 1 to 100 microns, and that sedimentation will give you your size distribution. But if they're very small particles, then you can use centrifugal sedimentation. Optical microscopy is also commonly used. So use microscope and then image analysis, and that will give you between 1 and 40 microns. And if you use electron microscopy, then you can go to much smaller sizes. A very nice method, and that is very easy to use, and even in our department we have one such method, and that's laser diffraction, and that gives you a really wide range. Then there's gas absorption, and this is Coulter counter. So particles are drawn through a small orifice, and then the variation of the charge for across electrodes which are put across the orifice is measured, and then you can count the particles. So the change in the charge depends on size and so on. So this is some electrochemical method for measuring size. So this is just a set of these, and you can go into the go on the web and you'll see many commercial systems which are available for measuring sizes. But size measurement is now quite a nice and standard way of doing it. But as I said, this will give you an equivalent diameter, but it will give you a range of sizes. And so, you need to characterize them not in terms of a size, but particle size distribution. Okay. So you'll not just get one size, but all these measurement techniques that I just listed above, they will give you something like this, that they'll give you a graph and they'll give you data also in the form of a histogram. So let's say W is the weight fraction of particles, and let's say dP is the particle diameter or the equivalent diameter. So then you will get something like this. And let's say if this is Wi, and let's say this distance, this diameter is dP of I, and this diameter is dP of I plus 1. So this is the histogram, and here your Wi is nothing but the weight fraction of particles in the size range between dpi and dpi plus 1. So dpi, maybe this is 50 microns, and dpi plus 1, depending on the size of this interval, maybe 100 microns. So between 50 and 100 microns, what is the weight fraction of particles? So that will give you. But The same way, we can also, instead of writing it in terms of weight fraction, sometimes you may want to write it in terms of n, which is the number fraction. And again, you may have, in general, this may not be the same as that, and you may get something like, I've just drawn it arbitrarily, it doesn't matter. And here now, Ni is not the number fraction, is not the weight fraction, but it is the number fraction of particles in the size range. So really, you can characterize this, and all these measurement techniques will give you both of these things, and then you can sort of use this, and from this, as we'll see in the next class, first thing is that, of course, to say that Ni and Wi are related. So if you're given one, you can easily calculate the other, and then once you know either of these, you can calculate the average sizes. So you can calculate various kinds of averages, like the number average size, the volume average size, and so forth. So we'll do that all in the next class. Okay. So if there are any questions or comments, you can